The vacuum of space is not an empty void, but a complex, dynamic fabric that dictates the movement of every celestial body in the cosmos. For decades, the speed of light, denoted as celeritas, has stood as the ultimate sentinel and unbreakable universal speed limit established by Albert Einstein's special relativity. However, deep within the mathematical frameworks of general relativity, a provocative possibility emerged in 1994 that challenged our fundamental understanding of interstellar travel. Theoretical physicist Miguel Alcubierre proposed a solution to Einstein's field equations that suggested we might not need to move through space to reach the stars. Instead, we might move space itself. This concept, known as the Alcubierre Drive, does not violate the laws of physics by accelerating an object beyond light speed. Instead, it manipulates the geometry of space-time by contracting the fabric in front of a vessel and expanding it behind. This theoretical warp bubble would allow a spacecraft to remain stationary within a local patch of flat space-time, while the bubble itself moves at arbitrary velocities. Before we dive into the mechanics of space-time manipulation and the extraordinary energy requirements it entails, consider this scientific challenge. According to the current constraints of the Alcubierre model and the energy conditions of general relativity, what specific exotic property is required of the matter or field used to create a stable warp bubble? Is it A, a mass equivalent to the Sun compressed into a microscopic singularity? B, a field of negative energy density that violates the strong energy condition? Or C, a synchronized gravitational wave resonance generated by a binary pulsar system? Think carefully about the relationship between gravity and the curvature of spacetime. The answer is hidden within the complex physics we are about to explore, and I will reveal the scientific explanation at the end of our journey into the next frontier. The transition from theoretical curiosity to experimental inquiry began with the realization that spacetime is not a rigid stage, but a flexible medium. Einstein's general relativity tells us that mass and energy tell spacetime how to curve, and the curvature of spacetime tells matter how to move. In the Standard Model, this curvature creates gravity. However, Alcubierre's metric flipped the script by asking what kind of energy distribution would be required to create a specific functional curvature for propulsion. The primary hurdle identified by early critics was the sheer amount of energy required, originally calculated to be more than the total mass energy of the observable universe. However, subsequent refinements by physicists like Chris van den Broek and Harold Sonny White have suggested that by modifying the geometry of the warp bubble, S-wall, and its thickness, the energy requirement could be reduced to the mass energy equivalent of a spacecraft like the Voyager probe, or even less. To understand the secret experiment mentioned in theoretical circles, one must look at the White-Jude Warp Field Interferometer. This device was designed to search for a tiny instance of the phenomenon on a laboratory scale. The goal was to detect micro-warp bubbles, minuscule distortions in spacetime that might occur when an intense electromagnetic field is applied to a specific region. By using highly sensitive lasers to measure the phase shift of light as it passes through these fields, scientists hope to observe a tiny variation in the path length of the light. This would be the first tangible proof that space-time is not just a mathematical concept, but a physical substance that can be manipulated by human technology. While the signals detected have been close to the noise floor, they represent the first steps toward a technology that could one day render distance obsolete. The search for a way to power such a drive leads us to the strange world of quantum vacuum fluctuations. According to quantum field theory, empty space is actually teeming with virtual particles that pop in and out of existence. This creates a baseline energy known as zero-point energy. One of the most famous proofs of this is the Casimir effect, where two uncharged, parallel plates placed extremely close together experience an attractive force. This force arises because the space between the plates is too narrow to allow certain wavelengths of virtual particles to exist, leading to a lower energy density inside than outside. This effectively creates a region of negative energy density relative to the surrounding environment. Mastering the Casimir effect on a large scale could be the key to synthesizing the exotic matter required by the Alcubierre metric to maintain a stable warp bubble without the structure collapsing into a black hole. However, the path to the stars is fraught with theoretical dangers. A functioning warp bubble would not be a passive vessel. As it moves through the interstellar medium at apparent speeds exceeding light, it would accumulate high-energy particles like a cosmic snowplow. These particles would become trapped in the warp field, gaining enormous amounts of energy. Upon arrival and deactivation of the bubble, this energy would be released in a colossal burst of gamma rays and high-energy radiation, potentially destroying the very star system the explorers intended to visit. This is known as the Alcubierre radiation problem. Scientists are now investigating ways to tune the warp field to deflect these particles, or to use secondary magnetic shields to prevent the buildup of lethal radiation, a challenge that requires a much deeper understanding of how matter interacts with highly curved spacetime. As we look toward the future, the research continues at the intersection of high-energy physics and interstellar theory. We are currently in what many call the Galileo phase of spacetime engineering. Just as the first telescope revealed that the heavens were not perfect and unchanging, our current experiments are revealing that the fabric of the universe is far more pliable than we once believed. Experiments involving high-frequency gravitational waves and the study of topological defects in the early universe, such as cosmic strings, provide clues about how spacetime might be coerced into shapes that favor travel. This is not a clandestine government project, but the collective, open-source endeavor of theoretical physicists pushing the boundaries of what the laws of nature permit. We are learning that the universe may have loopholes, and the Alcubierre metric is the most promising map we have for finding them. We return now to the fundamental question posed at the beginning. To create the localized contraction and expansion of spacetime necessary for a warp bubble, one must utilize a field that possesses a very specific and unusual property. The answer to our quiz is B, a field of negative energy density that violates the strong energy condition. In general relativity, standard matter has positive mass and creates attractive gravity. To push space-time apart to create the expansion effect behind the warp bubble physics requires exotic matter or an energy field with negative pressure. While this sounds like a violation of reality, quantum field theory has proven that such states are physically possible. The realization that negative energy is a reality provides the foundation for all future research into space-time engineering. The journey to the stars may not be about how fast we can burn fuel, but how well we can understand the stage upon which the cosmic play is performed. And that's a wrap on another journey into the amazing world of science. I really hope you enjoyed today's exploration as much as I did. A massive thank you to every single one of you for tuning in and being part of this incredible community. Your curiosity and passion are what make this all possible. If you found this video interesting or learned something new, I'd be so grateful if you could hit that like button. And if you haven't already, please consider subscribing to Next Frontier Science and ringing that notification bell so you never miss our next adventure. Your comments and shares mean the world to us. They help our channel grow and reach more curious minds just like you. I love reading your thoughts and ideas, so please drop a comment below. What topic should we dive into next? Until then, stay curious, keep questioning, and I'll see you in the next video. Thanks for watching.